Hello, friend. Welcome. My name is Derek Harder, and in this video, we're going to start working on our open source operating system, chapter 3 of our textbook. So this chapter, this is the chapter about memory management and the implementation of virtual memory in an operating system. So it's specifically in the XV6 teaching operating system that we look at in this class. So in this first video, I'm going to look at the hardware side of things. So we'll look at how RISC-V implements, provides so that you can use what are known as page tables to set up a address space and to translate from a virtual address space into a physical address space. And then the next video after this, next video or two after this, we'll look at then how the hardware page table mechanisms are used in order to manage memory and to set up a page table for the kernel and to set up page tables for the individual processes that the operating system is managing. So if you're ready, let's go ahead and get started. Okay, so first, just a word about page tables, what this mechanism is, how it's used. So page tables are the most popular mechanism through which an operating system provides each process with its own private address space and memory. Okay? So, if you implement an operating system on a different hardware architecture than RISC-V, it'll still have its own paging mechanism that will work essentially the same as we talk about here in this video. So page tables basically determine what a memory address means. Okay, and I can't emphasize this enough. I'm sure I've said this before, but you should understand that every time, once you're in a mode of the hardware that's using page tables, every time a memory reference is made, the hardware at runtime converts that reference to a memory address from the address space, looks it up in a page table to come up with a physical the physical address that's actually going to be accessed for the read or the write that was requested. Okay, so that translation happens dynamically. It happens at the hardware, but that does require some memory access because these page tables actually are going to be created by the operating system, but they're going to be put into RAM, into main memory, right? So to do this translation from a virtual address to a physical address requires memory accesses to successfully do this, okay? But anyway, I mean, that runtime translation is what determines what a memory address means whenever we try to reference, to read or write some byte of data to memory. So the operating system can set up page tables any way it wants to allow or disallow a process that's using a page table to be able to access physical memory. So they can access some parts, but not other parts, depending on what is set up in the page table by the operating system. So, these page tables basically allow for isolation, security. They allow to set up processes that can't, in theory, interfere with one another. Because they're isolated in their own address space, they can't see the address space of other processes unless they explicitly ask to do something, share memory, or to communicate with other processes on the system. This is the basics. This isolation provides the basis to allow for multiplexing. So to do time sharing, to share the CPU, to share physical memory. So in general, to allow multiple processes to run concurrently and access and share the resources safely in the computing system. Isolation provided by page tables or virtual memory like this allows for the illusion that each process has full control of memory. It doesn't see or know about any other process. It doesn't have to worry about processes messing with its code or data in its address space. They shouldn't be able to see that or mess with it. Okay? So page tables provide a level of indirection, so this also allows us to do some tricks which are used by XV6 and typically used by most operating systems to do similar things. So the main one being that there is actually a single page that gets mapped into all of the processes' address spaces. Okay, so there's only one actual physical page of memory that holds this trampoline page, but all processes will have that mapped to the last page of their virtual address space. And this will be for the next chapter when we start talking about traps and things. This is where the initial transition from supervisor to user mode and user mode back to supervisor mode happens on this trap wing page using this mapping trick. Some other things that are used by XV6, also used by other many operating systems. We can map in unmapped pages in order to guard stacks, so that if a stack grows too big and needs to grow onto a page that's actually unmapped, this will cause what's known as a page fault. And so some operating systems would just grow, would add another page, put it into the virtual address space so the stack can dynamically grow as needed. XV6 just will, this will cause a fault, and it will just kill the process, saying that it's outgrown its stack. Stack's too big; it can't do anything more. The use of this page table also allows us to access, allocate memory lazily, and also, by the way, we can also allocate the page table itself, as we'll talk about, lazily. So we don't have to allocate and set up everything up front when a process is created. We can do it basically on-demand paging or on-demand memory allocation. So the RISC-V instructions, both in user mode and kernel mode, so only in machine mode is this page table translation not done. So once you switch into supervisor mode, every reference is going to a memory address. It's going to go through this translation process that's described here. So all instructions that do like reads and writes are going to be manipulating virtual addresses. So RAM, you should have this mental model that physical memory is indexed by physical address. So we'll call this the physical address or the physical page number, PPN. So the RISC-V page table maps each virtual address in the current page table virtual address space to a physical address. And as a first approximation, you can use this as a mental model, although we're going to immediately kind of complexify this a little bit in the next slide here. Okay, so XV6 uses, there's a couple of different modes that RISC-V provides of page tables. It uses the kind of the smallest 64-bit one called SB39. So there's actually like a SB48 and an SB57. So I won't describe any of those. So for 39, we're really only using the low 39 bits of 64 bits are used for the virtual address space. Okay? And by the way, the observant student might remember that we said that it was actually 38 bits in the previous lecture that we talked about, was the number of bits that were used for addresses by XV6. So the SB39 mode uses 39-bit addresses here of the possible 64, so leaving 25 unused. XV6, the most significant bit, just always leaves as a 0 because that simplifies. It keeps from needing to do some sign extension or worrying about some things. So it actually only uses 38 and always has the most significant bit 0 of these 39. So that's why the top of memory from the virtual address space is 2 to the power 38 minus 1 for XV6 systems. But this is still plenty big. So that means that we actually have 39 bits. Remember, each one of those 39 bits could address a single byte of memory in the virtual address space. Or since we're using 4K page tables, so we use a 12-bit offset. Every page is divided into 27 bits for the page number and a 12-bit offset, meaning that each page has 4 kilobytes or 4,096 bytes on it. All right. But that's still a huge addressable space, even just talking about the virtual address space. So there's 134 million plus pages that 27 bits could could potentially address. And remember, each page is 4 kilobytes, so that works out to 512 gigabytes. So half a terabyte of addressable space here. Right. So typically, computers that we work with might have terabytes of hard drive space, but they're only going to have maybe hundreds of. Well, they might have 64 or 128 gigabytes of memory, but this would still be able to easily address all of memory. A space of that size, basically up to 512 gigabytes. But anyway, that's only the virtual address space. Okay, so again, this is the translation process that's shown on the figure on the right-hand side here. So every time, like a read is done, we're going to get a memory address of that read, and it will take these 27 bits, and we'll use that as an index into a page table. Okay, so here we're showing just a flat page table. We're going to show what's really done in SV39 on the next slide here, right? So, but this 27 bits would be some number between 0 and 2 to the power of 27 minus 1. So we just take that, you think of that as an index into the page table, right? Where the start of this page table is going to be held in a register. Right, so one of those special registers that can only be modified when we're in supervisor mode holds the address of the start of this page table. So you take the start of the page table, add the index of these 27 bits, that gives you a location of what's known as a page table entry. All right. So in the page table entry, we're going to have each page table entry as we'll see on the next slide, is actually 64 bits long, but we only use 44 bits to represent a physical page number. And then these other 10 bits are going to be some flags. I'll talk some more about the flags in a second here. So that means that the physical page number is actually combined with the offset, so we end up with a 56-bit physical address. Okay, and again, 56-bit. There's a little bit of room for growth in a 64-bit system. We could get up to use the full 64 bits for an address, but 56 bits is, I think our textbook mentions it, 56 bits is enough to actually address a physical memory that's 65,000 terabytes. So not 65 terabytes or 100 terabytes, but thousands of terabytes. So this is still really big here. So real quickly, one downside of thinking this is a flat page table is we would actually need 134 million page table entries. So for every page table we want to support, we need that many entries in memory, and we couldn't actually have two, so if I want to have two different page tables for two different processes, I couldn't have them overlap in any way, because this has to be contiguous if you think of this as a flat page table. And that doesn't work, or at least it doesn't work easily, right? So typically, instead, for modern hardware, page tables are going to operate on using multiple levels of page table lookups. Okay, so the SV39 standard uses a 3-level tree for the page table, and I think 48 uses a 4-level page table tree, and SV57 uses a 5-level page table tree. So talking about how actual 3-level page table works, but before I get to that here, we ran across the RISC-V.header file. So just to remind about some numbers here, right? So all of our pages are going to be 12 bits inside, to the 12, so an offset of 12 bits. So that means that we actually have 4,096 or 4 kilobytes on each page in our paging system here. So, if you look in the RISC-V.H, so that means that we have 4,096 bytes per page, and we're using 12-bit offsets, which means that if I need to shift to get the offset out of there, I'm going to have to shift 12 bits so I can have the 27 bits at the bottom of my variable in order to figure out the page number. And again, I'll remind, this was the file that had that max VA that we talked about in the previous video. So the maximum virtual address that we can use. So we really are using the SV39 standard, which we're going to use 27 bits for a page number and 12 bits for an offset. But we don't use the most significant bit in the first level of the 3-level for some sign extending, in order to simplify some things. So we're really only using 38 of the possible 39 bits here for address. One other thing I mentioned here before I move away from the code, so each of these page directories in this 3-level page table tree that we're going to talk about here, it lives on a single page. So there's 4,096 bytes. But each page table entry needs 64 bits or 8 bytes. So that means that since we need 8 bytes for page table entry, we can get 512 page table entries on each one of these individual page directories, like our figure calls it here. So let's look at this. Explain what happens here. So for every memory reference, read or write, we're going to take the address that's referenced. We're going to take these 9 bits, the level 2 9 bits, combine that with whatever is in the satp. Okay, so this is the thing that holds the location of the top level page directory entry for the current page table. And every time we want to switch to another process, this register, satp, which stands for it's the page table something. So every time we want to switch to a different process, this has to be changed to point to the correct top level page table entry. Okay? So notice we have to do one memory access. So we combine whatever's in this register with those 9 bits that will give us an offset into this page directory. Okay? And by the way, 9 bits means that the number can be from 0 to 512 minus 1. To the 9th is 512, right? So that's an index. So, whatever those 9 bits represent, that gets added to the addresses. And here, that is used to look up the page table entry, right? Of which the bottom 10 bits are flags. I'll come to those in a second here. But then the next 44 bits here are the physical page number. And then we do that all over again. So for a 3-level hierarchy, this becomes the physical page number, which is the base address. Then we use these 9 bits for an offset, and that gives you the level 1, as it's called in the XV6 code here. And that will give us another lookup to the final directory, which gives us the access to the final physical page number and offset. Okay? So here, when we look this up, this will give us the final 44 bits for the final actual physical page number, not a location of a page directory in this tree here. And that gets combined finally with the 12-bit offsets to make the actual physical address. Right? So again, remember, all of this happens in hardware, right? So we do like a read, give it a 39-bit address. It ignores these bits and uses those to do 1, 2, 3 memory accesses, and then finally a 4th memory access. Okay, so you may or may not have thought about that, but that's kind of a bit of a problem because accessing memory is much slower than accessing registers on the CPU usually. So there's usually special things that have to be part of the hardware called these translation look-aside buffers, which act as a cache specifically for the paging hardware in order for this to be efficient enough to actually be usable in practice instead of being bogged down by 4 memory accesses for every reference to memory that we want to make when we translate it from a virtual address to a physical address. So although the CPU basically walks this 3-level structure like I was just describing, and it does that at runtime to translate every address reference to a physical address, the operating system has to know about the structure in order to set this up and maintain it for the hardware, right? So it is the responsibility of the operating system to create the page table structures for each page table that it wants to maintain, right? And essentially we've got one page table for every process plus a special page table for the operating system kernel itself that it uses. So, number of processes plus one page tables are being maintained and switched between those by switching the satp page table pointer here. So on each one of these page directories in this tree structure page table, there's 512 page table entries, and that's what this is down here, right? So 44 bits are the physical page number, the PPN, but then these other 10 bits are flags, right? So most of these are relatively self-explanatory. So the most important is the least significant bit, whether that entry is valid or invalid. Okay, so for example, it's maybe easiest to understand down here. So if we get down to here, but that page number showing up as valid, that memory wasn't actually allocated yet. Okay, so we've got an entry in the address space, but we never actually have physically allocated a frame out in memory to point that virtual page to. And then, but the operating system can use all these to set up other isolation and protection mechanisms. So, things that only have code should normally only be set to be readable, so that we're only reading code off them and not trying to modify pages that hold code. Things that have data need to be writable and readable. Things that are code should be executable, but things that are just data shouldn't normally be executable. So you can set up pages that are only allowed to be accessed when we're in supervisor mode. So, most pages, when you allocate them for a process, are going to be set only to be accessed when you're in user mode. So that, again, a trap or an exception will be thrown. I guess the opposite is the other use of this is more useful. So you set it up so a page can only be accessed when you're in supervisor mode, so that you have particular pages that a process might be able to see, but they shouldn't be able to modify or write them or access. And then these are useful for telling whether a page has been actually read from, or whether a page has actually been written to. The operating system usually needs to know these in case it's going to kick out a page from memory to reuse it for something. So to tell a RISC-V CPU to use a page table, the kernel has to write the physical address of the root page table of a page table to the satp pointer. Right. So, and initially, I'll show this in a second here, but a one page table is created that the root that the kernel uses that has access to all the physical memory, but we're still using a page table once we get into supervisor mode. We briefly talked on these in previous videos, although we didn't show these. But so, for example, the initially paging starts off as disabled. We did mention that before. Then let's look at the kvminit heart here in the kvminit. So this is where the kernel page table is created and enabled. And then later on, as part of process creations, I actually showed that a little bit, or at least showed in the alloc process that a page table, we didn't look at the actual code that created the page table, but each time a process created, the operating system has to set up a new page table for the process. And each time we switch to a new process, it's going to be setting that satp register to point to the page table for the user process that needs to be currently running. So let's look back at start.c, which we looked before. This is called by entry, jumps to here. but we'll just remember that paging is disabled initially, right? So basically, for the RISC-V hardware, if you write a 0 to the SATP page table pointer, it will have paging disabled, right? So any reads or writes will just directly go to the physical page table instead of going through this translation process. So if you go back and look at the main function that start jumps to that we've seen previously, it calls KVM, so virtual memory initializer, and the virtual memory initializer for the hardware thread, right? So we only need to initialize, create one kernel page table. So this is only called on CPU 0, but we do have to turn on paging for all CPUs, right? So this is called both here and here, the KVM init heart. If you look at kvminit, so I'll just follow that, notice it calls kvm make. Doesn't do anything, but the result of this is going to create a page table of the structure needed. It's going to return the address of that page table, and we just always remember that from then on as what the location of the special kernel page table that should have access to all of physical memory. And we'll talk more about this, I think, a little bit in the next video. But basically, you can see that it's setting up, using this KVM map, things for the, device spaces, so I/O and the UART, and the PLIC, we'll talk more about. Has the trampoline page mapped in here that's going to get mapped and visible to all user processes as well. So this page will be shared in all address spaces that it creates, and other stuff. So if we look at these So I won't go through all of these. Let's just look at one instance of what kvm map does. But it basically starts by allocating the root page directory. So this just allocates a single page. If you look at kalloc, there's a free list that was set up before this point. It accesses something from the top of the free list. It just returns that. So one page, 4096 byte page gets returned by calling kalloc there. And then this just zeroes out everything. So everything is initially 0 in there. So let's look at kvmap. So this is mapping. This is being called to map all of these are basically creating page table entries in the page table that we just allocated the root of our page table for, right? So like if you look at kvmap, I'm just hitting F12 to go to these. This mostly just calls map pages, right? So all the hard work is done in map pages. So this, if you look carefully at it, this is doing the three-level structure walking of our three-level page table entry, okay? So it's a little bit beyond for me to step through it one by one, but yeah, I would encourage you maybe to at least spend a little bit of time on what this map pages is doing. So this can basically tell, using walk here, whether we start at the top level of the tree, and this will, if you look at this code closely, this will, at most go 3 levels. If it gets to one where the page table entry is invalid, it will create it as needed here, and then finally end up mapping in the page table entry once we create it in the page table here. Okay, so once the initial page table for the kernel is set up, we do switch into we do enable paging by setting that SATP register to be something other than 0. So we showed that happening basically after the kernel page table is created. So at that point, subsequent instructions go through this translation process, and each CPU has a separate satp register, so they can each actually be running and translating from different page tables, right? Which makes sense because each CPU could be running a different process or could currently be running a kernel system call, right? So each of those has to have a different page table enabled in the satp depending on whatever's currently running on the CPU core. So from the kernel's point of view, the page table is just data stored in memory, right? So whenever the operating system has to set up a page table or maintain a page table, it's just maintaining memory, right? So it's just modifying, maintaining stuff in memory in order for this translation at the hardware level to correctly happen every time memory reads or writes or not. Okay, so that's it for this video. Just to summarize the topics that we touched on in this video. So, the page tables are a very important mechanism. They provide the basic mechanism by which the operating system implements isolation and multiplexing of resources, such as time sharing, in order to multiplex and share the CPU among multiple processes. So, in order to successfully implement isolation and multiplexing, the CPU architecture must support runtime translation from a virtual address to a physical address. Okay, so and the most common way this is done is through what are known as page tables, which provide a type of virtual address paging. Okay, RISC-V uses the satp register. So anytime that the CPU is running in supervisor or user mode, every reference to memory goes through this translation by starting at the page table directory page that the satp is currently pointing to. Right? XV6 uses this SV39 standard. There's some other standards that RISC-V hardware can implement, but the SV39 is a 3-level page table tree. So up to 39-bit virtual addresses. So that means that 2 to the 39 bits is the maximum virtual address space that could be addressed. Actually 2 to the 38 in XV6, since it doesn't use the most significant bit. And whenever you have a page table as a multi-level tree like this, it requires a memory access for every level of the tree, plus a final one to actually read or write the physical address once it's translated that was asked for. So that requires other hardware support in order to be efficient enough to actually be used in practice. So you have to use heavy caching of the page tables. That's if you ever hear a look aside translation buffer. That's what's being done here, is this caching of the page tables entries. So in this class in XV6, we're going to be exclusively using 12-bit offsets, which means that all pages are 4096 bytes. So some hardware supports different page sizes. And I believe that there might be standards for RISC-V where you can use different page sizes as well. But a standard one is a 12-bit page size, which means that you have 4096 bytes on every page. And so each page directory in RISC-V is held on a single page. So that means, since each page table entry is 64 bits or 8 bytes, that means you can have 512 page entries on each page directory. Okay, so that's for this video. As usual, leave me comments or send me emails if you have questions or things. And I hope to see you in class or in the next video.